Why can't I use just one end mill in both aluminum and Inconel? That's a fair question. I mean, carbide is tough, the tools look similar, and coatings today are cutting edge. So why not just run one premium cutter across the board and simplify life? Let's discuss this further. Now here's the deal. The question about using one tool for both materials, it's not just about whether the carbide itself can handle it. The real issue, the one that determines whether the tool will succeed or fail, is the tool's geometry. So let's do a deep dive into tool geometry by looking at two materials that sit on nearly opposite ends of the machining spectrum, aluminum and Inconel. These two materials we are discussing behave so differently when machined that they demand fundamentally different tool designs. What works beautifully in aluminum with a low flute count, relief type, and wide flutes with a high rake would not be suitable for Inconel. And if you bring Inconel geometry into an aluminum tool, you're going to get material adhesion, a noisy cut, chatter, and a poor finish. Contrasting how these materials cut is exactly why geometry matters so much. Let's start with the big mismatch. Aluminum is soft, it's ductile, it cuts easily, but it loves to weld to the tool if you don't get the application right. So what do you need? You need sharpness, you need speed, and effective chip evacuation. Inconel is the opposite. It's heat resistant, it work hardens, and if you rub it, the tools are going to fail quickly. You need a tool that's built to be tough, to take the heat and hold up when the cutting edge is under serious stress. Yes, both of these materials are cut with solid carbide, but the way they behave during machining is so different that not one single geometry can be optimized for both. A tool that is perfect for aluminum will just snap or rub in Inconel, and a tool that's tough enough for Inconel is going to be noisy, give a poor surface finish, and likely clog up in aluminum. And sure, a general purpose cutter might get the job done in a pinch, but if you're chasing performance, part quality, or tool life, you need to match the geometry to the material. That's non-negotiable. This applies across many materials, even beyond our examples of aluminum and Inconel. Let's focus on geometries that are optimal for materials like aluminum. When you're machining aluminum, it's all about moving fast and getting those bigger chips out of the way. So what does a solid carbide tool for aluminum look like? First, you've got a high rake angle. We're talking 10 to 20 degrees. That lets the tool shear through the aluminum clearly without plowing through it. You also want a sharp edge, preferably with no hone. You're cutting a soft material here, so you want a sharp edge to slice through it like a knife through butter. Then there's the flute count. 2 or 3 flutes is ideal in aluminum because you're forming big, thick chips. You really need the space there to clear them out, or they're going to get stuck and clog up the tool in the flute. A high helix helps too, 35 degrees or more. That gives you faster chip evacuation and keeps the cutting zone clear. And finally, the coating and finish. A coating such as Dynamite B from SGS and polished flutes can really step things up in terms of performance. These reduce chip adhesion, minimize friction, and help increase tool life. Now take that same geometry and throw it at a material like Inconel. That tool's going to chip and break down before you possibly even finish a single pass. It's just not built for that level of heat, stress, and force. So what's the secret to machining materials like Inconel? A major key to success is choosing tools that are optimized for strength and heat control. Your tool has to be able to take that punishment without giving up. The rake angle comes way down to 3 to 8 degrees. A lower rake strengthens the edge and reduces the chance of chipping. You want a sharp or slightly honed edge where that minimal hone adds durability and keeps the edge free from microfracturing under stress. True sharp tool will take a beating initially, but it will quickly bed in and wear appropriately throughout that cut. The flute count goes up to 4, 5, and sometimes even more. Utilizing a 9 or 11 flute tool can really help improve productivity in certain applications, especially as this gives you a stronger cross section and helps stabilize the cut. A thicker core is key. That thick web means less deflection, which is crucial when you're buried deep into a part or taking a longer axial cut. And for coatings, you want to be looking at coating that's designed for thermal stability, oxidization resistance, and durability in harsh, high-temperature environments. They help protect the edge and extend tool life, and this tool geometry isn't about speed, it's about survival. You're building a tank, not a sports car. Now, let's look into some of the stuff that doesn't really get talked about nearly enough. And I'm talking about higher level questions that machinists are asking but don't always get answered. Starting the advanced geometry discussion, let's talk about variable helix, chip breakers, and micro geometry. In Inconel, a variable helix, unequal flute spacing, helps break down the harmonics as it cuts down vibration that can reduce chatter in long axial cuts. A chip breaker helps break up the chips into smaller pieces, so the tool load is also reduced throughout the cut. You're also able to manage smaller chips far more easily than a longer chip that can easily nest and cause issues with tool break. But in materials like aluminum, these extras can sometimes backfire. Variable helix may reduce flute volume, and unequal spacing doesn't really offer any significant benefit with the usual 2 or 3 flute geometries used in aluminum. So again, it comes down to purpose-built geometry for the application. And what about micro geometry? Things like land width, relief type, and edge breadth. These tiny details make a huge difference. In Inconel, eccentric relief increases flute strength and reduces friction. In aluminum, those same features can cause drag, smearing, and built-up edge. Here's a popular question: is there a coating that works both well in aluminum and Inconel? Honestly, not really. Let's talk about wear and analyze it. In Inconel, you're looking for flank wear and notch wear at the depth of cut line, crater wear on the rake face, or thermal cracks. If you hear a pitch change or start seeing the surface finish go downhill, those are early warning signs that your tool is wearing. In aluminum, it's all about built-up edge, chip welding, and flute packing. If you see material stuck to the tool, or if the edge goes dull quickly, there's the geometry telling you that it's overloaded or misapplied. Machining strategies and tool path optimization go hand in hand with geometry when machining difficult materials. Now, Inconel needs a different approach. Try to use dynamic tool paths with low radial and high axial engagement. Work with appropriate chip loads, higher for low flute count tools and lower for multi-cut tools, and maintain the chip load throughout the cut as to not excessively change the load on the tool. If you do go into a slot, take consideration to the axial depth and make sure there's as much coolant around the cutting area as possible. Aluminum is quite the opposite. Crank the RPM, run a large step over as the application allows, and use those 2 or 3 flute tools to increase that chip load. And always watch your stick out. In Inconel, stick out amplifies vibration and leads to early failure. Even in aluminum, it can cause chatter. Shorter stick out is better whenever possible. Let's say you're a shop with a hybrid or niche scenario that runs mixed materials. You might ask, is there a compromise tool? There are 4 flute tools out there with mid-range rake, polished flutes, and multi-layer coatings that can do okay in both, but you won't be exceptional in either. Use them for short runs only. They're a great option for smaller job shops who are constantly changing jobs, materials, and setups. General purpose tools usually have a middle-of-the-road rake angles, moderate flute count, and a variety of coating options. They're a great option, but if you're in production and care about repeatability and performance, then geometry-specific high-performance tools are the right move every time. So back to the big question: can one solid carbide end mill handle materials that are extreme ends of the machining spectrum, such as aluminum and Inconel? In a pinch, yes, but it won't do either of them well, and it's not something we'd recommend. Geometry matters, and when you look at it closely, it tells you everything you need. High rake angle, wide flute spacing, sharp edge, that's an aluminum cutter. Lower rake angles, more flutes with a thicker core, that's a tool for Inconel or other similar materials. Don't fight the machine, don't fight the material, and definitely don't try and fight the tooling. Read the geometry and let it guide you to the right decision. Thanks for joining us today on Tips and Chips. If you found this helpful, please like, subscribe, and hit that notification bell. Got any questions or tips you'd like to share? Leave us a comment below, as we'd love to hear from you. Need help? Visit the links in the description for more resources. And as always, keep those chips flying.